Hello, welcome to this video. Today I will talk to you about the RuleGrowth algorithm. It is an algorithm to find some patterns in some sequences that we call the sequential rules. So we have sequence, we want to find some rules, and I will present some algorithm to find these patterns. So first I will give you a brief introduction about this. So in real life, there are many databases that contain a large amount of information with time. So for example, maybe you have data about what some people do every day, what the people buy in a store. So this is some data with time. Or it could be about the price of the stock market every day. So we have different price and also there is time. So there's a lot of data with time, or more generally with some sequential information. That means it's not necessarily about time, but there's some order, some sequential order between some events or elements in the data. So for example, in a text we have some sentences with some words, and there is some order between the words. So it is some sequential information. It is not about time, but there's also some order between the words. So in data mining, if we want to analyze the data, find some pattern, something interesting, we want to design some algorithms that can find the useful patterns in this data with time or sequence information. There are different kinds of patterns that we can find in the temporal data, such as the repetitive patterns, some trends, some sequential patterns, and so on. In this talk, I will talk to you about one type of patterns that we call the sequential rules. Okay. So in this paper, we are interested by what we call the data. We call the sequence database. That means it is a database where we have many sequences. And a sequence, it is some ordered list of events or symbols. So we have many sequence of events or symbols like text, and we want to find some patterns that appear in many of these sequences. So let me show you some example of sequence. Okay, first. So a sequence of events or symbol, it can be, as example, a sequence of web page clicks. That means if you go on a website, you click on different web page, and all the web pages that you visit is a sequence of web page. Another example, you can see on the bottom, a sequence of activities, what you do during the week or during a day. First you go home, then you go to cinema to watch some movies, you go to a museum, and so on. So it is a sequence of activity. It is also a sequence of events or symbols. Another example is the sequences of purchases, what some people buy in a store, for example. So maybe you go to the store, you buy a computer, then you buy a monitor, you buy a router, and so on. And maybe we have many sequences like this for different customers, and we want to find some patterns like people who buy computer then will buy a monitor or router, and so on. Okay, another example of sequences, they are the sequences of words, like in the text. So in the text there's some order between the words, and we can see each sentence as a sequence of words. Then maybe we want to find some patterns in the text about the writing style, how the people write the text. So maybe when we write something like R, then it is always followed by U, RU, or many times in the text. We can find patterns like this. Okay, so in my introduction, I talk about the type of data we are interested in. These are the sequences of symbol or events. So I will give you more formal definition, what we call a sequence database. Let's say that we have a set of symbols we call A, B, C, D, and so on. So the symbols could be some events or words in a text, or events like like for shopping and so on, as I showed you before. And we say an item set is a set of items or symbols that appear at the same time. And a sequence is an ordered list of item set. So let me show you an example of a sequence database. We have a table at the bottom. This table has 4 sequences. And the first sequence, let's look at sequence 1. It contains the item set AB. That means A and B appear at the same time. Then it was followed by C after. Then after there was the symbol F or event F, followed by G, and followed by E, and so on. We have another sequence, sequence 2, AD together at the same time, followed by C, followed by B, followed by A, B, E, and F at the same time, and so on. So this type of data, as I said, can be used to model many different types of data. Okay, so what can we find in such data if we want to find some patterns to analyze the data? We can use a type of technique. It's called sequential pattern mining. The idea is, as input, we have a sequence database, as you can see on the left, what I showed you before. Okay, a database with 4 sequences. And the user needs to set a minimum support threshold, like minimum frequency. And the output is all the subsequences that have a support greater or equal to the minimum support. That means all the subsequences that appear at least min sub times in the database. So let me show you this with the example at the bottom. We have the sequence database, as you can see, with 4 sequences. We set the parameter, the minimum frequency or support, to 50%. That means we want to find all the patterns that appear in at least 50% of the sequence of the database, that appear at least twice in 2 sequences of the database. So here, for example, we find the pattern A has a support of 100%. That means it appears in all the sequence of the database on the left. So here we have A in the other sequence, A again, and A again. So A appear in all the sequences, 4 out of 4, so it is 100%. Now let's look at the second pattern, A, followed by B and C at the same time. So here we have A in the first sequence, followed by B and C. So it appears 1 time. In the sequence 2, we have A, followed by B and C together. So it appears twice. In sequence 3, we have A, but then we don't have B and C at the same time. So it does not appear here. And then in the fourth sequence, we have A, but we don't have B and C together at the same time. So the support of A followed by B and C together is 50%. That means it appears in 2 sequences out of 4 sequences in the database. So 2 divided by 4 is 50%, and so on. So if we use the sequential pattern mining, some algorithms like this, we can find many patterns in this database. We call the sequential patterns, or the frequent sequential patterns. The patterns appear many times. So there have been a lot of paper about this, but there's some limitation. I want to talk to you about the problems with this. Actually, sequential pattern mining is not very useful to make some prediction. For example, consider we have a pattern X followed by Y. This pattern can appear many times in a database, as you can see here on my slide. So we have X followed by Y, X followed by Y twice. So maybe we think that X followed by Y appear many times in the database. So if we have X, we should predict that Y will appear after. But if we only look at this pattern, it will be misleading. Because if you look carefully, X always appear in the database. And actually it is only followed by Y 50% of the time. So X appear 4 times, but is only followed by Y by y twice. So actually, it is not a very strong pattern. Although it appears many times, if you look carefully, you find that x is not always followed by y. So if we only look at the pattern, maybe we take the wrong decision, or we take the wrong conclusion about the data. So if we want to make predictions, it's not very good to use these patterns. We need also a measurement of the confidence that if x will occur, it will be followed by y. We need to have some measure about this, how likely it is that x will be followed by y. So we don't have this in sequential pattern mining. So a solution that was proposed is called the sequential rule mining. That means instead of finding the sequential patterns, we want to find some patterns also with the time or the sequential order, but it will be the form of a rule. So for example, what we call a sequential rule is a type of sequential patterns that has a measure of confidence. A rule will have the form x imply y, x arrow y imply y. That means if you have x, it will be followed by y, okay? And it will have two measures. We call the confidence. How strong, if we have x, how likely it is that it will be followed by y. And we have a support also, frequency, how many times it appears. So maybe we have a rule like this: bread and milk. If you buy bread and milk, later, after, you will buy some coffee. So here the confidence is 75%, for example. That means most of the time, if you buy bread and milk, you will buy coffee after. So if we have the confidence, it's very useful to make some prediction. It's more useful than the sequential patterns. So if you know about association rule mining, maybe you think this is like an association rules. Yeah, it's true. Actually, it's very similar, but here we also have the time, the temporal or sequential order. So we call this a sequential rule. So there have been several algorithms to find some kinds of different types of sequential rules, but many of them will only find the rules like this in a single sequence, not in a sequence database, like many sequences. So in this paper, we want to find the rules that appear in multiple sequences. Okay, so let me show you some idea about this. How can we find the sequential rules in multiple sequences? So Zaki, in 2001, proposed an algorithm called RuleGen. RuleGen will find the rule of the form x imply y, where x and y are sequential patterns. So I show you an example here. Here we have a database of sequences on the left about music, about some people buy some music from Vivaldi, Mozart, Handel, and Berlioz, and so on. And then we can find the rules like this. If you look at the first one, rule 1, Vivaldi followed by Mozart followed by Handel imply that the people will buy Berlioz later. Mozart followed by Vivaldi followed by Handel will imply that later the person will buy Berlioz again. Handel followed by Vivaldi followed by Mozart imply that later we'll see Berlioz after that. Okay. And rule 4, if we have Handel and Vivaldi at the same time followed by Mozart, then it will be followed by Berlioz. Or the last one, 6, rule 6, Handel, Vivaldi, and Mozart at the same time will be followed by Berlioz. So, something that we can observe about this algorithm by Zaki, is that it will find a lot of rules that are very similar. If you look carefully at these 6 rules, all of them have the same items or symbols. All of them have Vivaldi, Mozart, Handel, but different order on the left. And on the right side of the rule, it is the same item, for example here, but not necessarily always, okay. So one problem with this, it is that all these rules are very similar. Actually here I only put 6 of them, but there are 23 rows like this. And all these rules, although they are very similar, they will have different support and confidence for the values. So the rule 1 has support 33%, rule 2 16%, rule 3 16%. And for the confidence, also quite different. Although the rule 2 has 50% confidence, rule 3 has 100%, and so on. So we have many rules that look very similar but have the different measures. So it can be a big problem. These rules are actually too specific. So a solution that I propose in my previous paper, you can see at the bottom, is that we find the partially ordered sequential rules. That means we remove some of the order. All the rules that we have on top will become a single rule, like as you can see at the bottom. Okay, so the idea, we remove the order on the left side or the right side of the rule. So on the left side of the rule, we say there's no order, and on the right side we say there's no order, but the left side must appear before the right side. So we find only one rule instead of all these rules, and the rule you see here is say Mozart, Vivaldi, or Handel. That means in any order. You can buy Mozart before Vivaldi, Vivaldi before Mozart. Any order will be followed by Berlioz. So no order on the left, no order on the right, but what is on the left must be followed by the right. And if we do this, we find only one rule instead of all the rules on top. And the support is 75%. The confidence is 66%. And in our previous paper, we showed that these rules are actually very interesting, because if you find too many rules that are too different, like on top, all of them will have a small support. But if you put them all together, you will get a better overview of the patterns actually. And many times in real life, all these rules are just a little different. Actually, we can see them as the same. We can generalize. So that's what we did in the paper you can see at the bottom of my slide. Now, in the paper I talked to you today, I will present a new algorithm for this problem. So let me first give you more details about what is the partially ordered sequential rules. A sequential rule X imply Y is a relationship between two sets of items that have each one don't have any order. So X imply Y means any events or symbol in X appear before Y, but events in X or inside Y have no order. So we use two measures to find the good rules. The support is the number of sequences where X appear before Y, divided by the number of sequences in the database. And the confidence, the number of sequences where X occur before Y, divided by the number of sequences where X occurs. So the problem is to find all the valid rules, all the rules that have a support and confidence that are no less than some threshold, some minimum support, minimum confidence. So I will show you some example to make this more clear. Here you see the sequence database on the left. We have 4 sequences as before, and we set the minimum support to 50% or 0.5, and the minimum confidence to 50% or 0.5. So we find some rules, as you can see on the left or the right. So for example, if you look at the rules A followed by B, A followed by B has a support of 50%. That means it appears in 2 out of 4 sequences on the left. So let's have a look. A here, but not followed by B. In sequence 2, A followed by B, so 1 time. In sequence 3, A followed by B. So, and the last one, we don't have A followed by B. So A followed by B is 50% of the time, support 0.5. Now for the confidence, it is how many times we have A followed by B divided by how many times we have A. So A followed by B is 2 times, divided by how many times we have A. How many sequences have A? Okay, so here we have 3 sequence with A, so it will be 2 divided by 3. The confidence is 66%, or here we write as 0.66. Another example, if we look at A, the first rule, A, B, C, any order followed by E. Okay, so here we have A, B, C, any order followed by E, so one time. In the second sequence, we have A, B, C, any order. It doesn't matter B is after or before C. A, B, C is followed by E, so it appears twice. And A, B, C followed by E does not appear in the other, so A, B, C followed by E appear in 50% of the sequences. And then we can also calculate the confidence and so on. So I think this is clear. Okay, so how to find these patterns? In the previous work, we present 2 algorithms called CM rules and CMDO. The first one uses association rule mining to first find some rules, and then because association rules don't have the order, then it will scan the database again to keep only the rules that are the sequential rules. So I will not explain in details now. And another one uses an a priori based algorithm to find the rules. So again, I will not explain the details here because I want to show you the new algorithm instead. So one problem about these 2 algorithms is that they will start from the small rule and then they will combine 2 rules to generate the larger rules. We call it the generate and test approach. So they always combine the small rule to make the larger rule and so on. But by doing this, they can generate some rules that does not exist in the database. They can spend a lot of time to look at some candidate rules that do not appear in the database. So it's not a very, very good algorithm. It gives a good result, but in terms of time or memory, maybe it will spend more time than it should to find the result. So in this paper, we present a new algorithm we call RuleGrowth. It is inspired by the prefix span algorithm in sequential pattern mining, and it will generate some rules by starting from the small rules with two symbols or items. Then it will grow the rules to find the larger rules. So we call this rule growth because it starts from the small rules and then it will grow the rules and so on. So how it works, I want to explain how it works. So we have a sequence database, as you can see, and we set the minimum support, minimum confidence threshold. Now what we do next? First, the step 1, the algorithm will scan the database to calculate the support of each item, each single item. So we scan the database one time. We find that A appear in 75% of the sequences, B appear in 100% of the sequences, D appear 25%, and so on. Then we keep only the frequent items. So because we said the minimum support is 0.5, then D is 25%. So we know that D cannot appear in the rules that will have at least 50%. So we can eliminate D from the items. We don't need to consider D anymore. It cannot appear in the rule that has the 50% support. Okay. So then step 2. We take all pair of frequent items to create the rules with 2 items. So we have A, B, C, E, F left. So we combine A with B to make A followed by B, or B followed by A. Then we combine A with C, A followed by C, C followed by A followed by E, E followed by A followed by F, F followed by A. So we make all the rules that have 2 items. Here, for example, AB. And when we make this, we calculate the support and confidence of the rule. The support here of A followed by B is 50%, and the confidence is 66%, 2/3. So we keep all the rules that have at least the minimum support and confidence, and we output them, we show them to the user. Now we found all the rows with 2 items. We need to find the larger rows. So step 3. We'll find all the larger rows by recursively scanning the database to add some items either to the left side of the rule or to the right side to grow the rows to find the larger rows. So let me explain this. Here I put some picture to show some rows. We start from the empty set. That means we have nothing. Then if we have the row like A followed by B, we can do a left expansion or right expansion. So if we have A followed by B, we can add an item to the left like AC followed by B. We add the C. Or we can add an item to the right. So here we add a E to the right. So to grow the row, so we have 2 choices. We start from the rows with 2 items. Then we can add more items to the left or more items to the right to find the larger rows. And we do this recursively until we find all the rows that we want, that are interesting, have the minimum support and confidence. So we start from these simple rows with 2 items, then we make the larger rows and we calculate the confidence and the support. And if the confidence support are higher than the minimum confidence and minimum support, we output the rows. So adding an item to the left is called left expansion. Adding an item to the right is called the right expansion. Okay, so now I will give you more details about how it works to explain more. Okay, so when a row should be expanded, when we should add the items to the rows. So there's a very simple idea. We should only add an item to a rule if it has the minimum support. So if a rule appears less than the minimum support times, like less than 50% in my example, we don't need to make the larger rule. Because if we make a larger rule with a rule that does not appear many times, the larger rule cannot appear many times either, of course. Now another issue about this. Okay, how to choose the items that we should add to the left of a rule. If we have a rule X imply Y, for example, what are the items we should add to the left to make the larger rule? So there's a very simple idea. If we have a rule like A followed by B, what we should add to the left of the rule with A? Okay. So we should scan the sequence that contain the rule and note all the items that appear in at least minimum support multiplied by the number of sequences in the database before the last occurrence of Y. So I will explain what I mean. So if we have A followed by B, we want to add something to the left. So we look at the last occurrence of B in each sequence. So we take the last B in each sequence. So here in the sequence 2 there are 2 B. We take the last one, the last B, and we count the support of all the items that appear before the last B, and if they appear at least the minimum support, then that means it will make a frequent rule. We can add the item to the left side. So here for the rule A followed by B, before B in the first sequence we have nothing before. In the second sequence we have C, B, we have D, but they appear only once. In the third sequence we only have A before B, so we cannot add anything in this case. So in this example, no item can be added to the left of the rule. We don't need to look at what appears after B, because if we want to add to the left side, it must be before the last B in each sequence. So I hope this is clear. This is not a very complicated idea actually. Now I talk to you about the left. Okay, I will talk to you about the right. So how to choose the item to perform the right expansion of a rule? So it is very similar. We scan the sequence that contain the rule and note the items that appear in at least minimum support multiplied by the size of the database after the first occurrence of the left item set X. So if we have the rules like A followed by B, we want to know the items we can add to the right side of the rule. So we look after everything that appear after the left side of the rule, the first occurrence of the left side. So we look at the first A, and we count how many times all the items appear after the first A. So we find that in all these sequence after the first A, in 2 of them we have a C. So C appear in sequence 1 and sequence 2 after A. E appear after A, after A, after A in the 3 sequence where we have A. So E appear 3 times. F appear also 3 times. Here, here, here after the first A. So that means now we can do the rule A followed by BC, A followed by BE, and A followed by BF. So that's how we choose the item to extend the rules, to add more items, to do the right expansion. Okay, so I explained to you how to choose the item to expand the rule, but there's another problem we need to discuss. It is that, look at my picture here. Okay, we have the rule AB. If we add C to the left, we get AC followed by B. Now, if we add D to the right, to the left, sorry, we get ACD followed by B. But if we start from the same rule, A followed by B, we add D first, and then we add C, we will get the same rule again. Okay, so depending on the order that we add the items to the rules, we can find the same rule twice actually. So this is not good. If we do an algorithm to find the rules in the data, we don't want the algorithm to find the same rules twice, because we will waste the time to look at the same rule over and over again. Okay, so the solution to this is that we should only add an item to the left or right side of a rule if the item is larger than all the items already in the left or right side. So that means if we have AB, we can add C or we can add D, because C is greater than A, if we use the alphabetical order, of course. Okay, so we can add C, we can add D. Then here, if we have ACB, we can add D, because D is larger than all the items in AC. So it works. But if we have ADB, we cannot add the C, because C is smaller than D. So we don't follow the order of the letters, actually, the A, B, C, D, the alphabetical order. So if we apply this, we solve the problem that the same rule can be generated by adding the items in different order. Okay. Now, there's still another problem. Another problem about this, it is the same rule can be generated by adding items in different order of left-right expansion. So if you have the rule AB, let's look at the example. We add C to the right, to the left, then we add D to the right. Or if we start again from AB, we add D to the right first and C to the left. And still we get the same rule, AC followed by BD. So again, we don't want to have this problem. We don't want to generate the same rule many times. So the solution, we do not perform a left expansion after a right expansion. So we can do the left expansion, but when we do not allow to perform the left expansion after a right expansion. So after a left, we can do right or left. But after a right, we cannot do a left. So we cannot do, we cannot add C here, as you can see on the slide. So this will solve the problem. I will not do the proof here, but it's explained also in our paper. And if we do this, we'll never generate the same rule twice. It's very important. Okay, so about the implementation of our algorithm. So we start with the simple rules with 2 items, then we make the larger rules, as I said, and we scan the database to calculate the support and confidence. So if we want to make this faster, there are some optimization. The first one, for each rule x imply y, we can keep the set of sequence containing x, y, and x and y. So when we scan the database, we remember for X where it appears, in which sequence, also Y, and also X and Y. So every time we want to extend the rule, we don't need to look at all the database again. We know all the sequence that contain X, all of that contain Y, and all of them that contain X and Y. And we can also calculate the confidence very quickly with this, without reading the database again. And another thing, optimization too, a little bit more complicated. When we scan the database for the first time, we record the first and the last occurrence of each item in each sequence. So as I said, when we add item to the left or right of a rule, we need to know what is the first occurrence of the item or the item set, or the last occurrence. So we will keep this in memory for all the items. And with this, we can create the rules with 2 items very quickly. And when we make the larger rules, we'll also update this, the first and last occurrence, to generate the rule more quickly. Okay. Now, so I will skip other details about the implementation. If you are interested, you can have a look at our paper. And also, the code of our algorithm in Java is open source. You can find in our SPMF software. I'll talk to you later. So here we did some performance evaluation. We compared the new algorithm RuleGrowth with the 2 other algorithms, CMRules and CMDO. We used Java. We had 1 GB of RAM. And we use some public database about sequence. The first one is about sequence of click on a website, sequence of click, and this is about the protein sequence. So these different databases have different number of sequence, different number of items, different sequence length, and so on, different characteristics. So in such paper, we want to compare the performance of the algorithm. We want to see if the new algorithm is better than the others. So I will show you some result. Here we have the first database. We look at the execution time when we change the minimum support parameter. Here we have the number of rules that we find, and we have the memory also for all the algorithms. So we compare the 3 algorithms. We find our algorithms is the fastest. It is really faster than the other by a lot, actually. And for the memory also, we use much less memory than the other algorithms. For the BMS database is also the same. Our algorithm is the fastest. And for the memory also, we are faster. Okay, so this is if we change the minimum support parameter. This is the other database. It is a little bit similar, so I will skip. Now, if we change the minimum confidence parameter, again, here we have the time, and our new algorithm does not use the confidence to reduce the search. So it does not change anything for our algorithm, but the algorithm called CMRules, if we change the confidence from 0.3 to 0.8, it will improve the speed of this algorithm. So we only change the confidence for this algorithm, and the 2 others, they don't use the confidence to make the algorithm faster. So we still find that our new algorithm is the fastest in terms of time. So in conclusion, in this presentation, I present a new algorithm to find the sequential rules that appear in many sequences. And also our type of rules is the partially ordered sequential rules. We think these rules are better. Actually, in another paper, we use them for prediction, and we find they give better result than the other sequential rules I talked to you before. So our new algorithm outperformed the previous algorithm in time and memory usage. If you want the source code and the database we use, all of them are available in our SPMF software, which is open source. You can find the website here. But also, if you just type SPMF in your search engine on the web, you can find the website very easily. Just type SPMF. It has 150 algorithms to find patterns in a sequence or database, a transaction, all kinds of patterns, rules, periodic patterns, item set, sequential patterns, and so on. So this is the website of the software. If you go there, you can go to download, to click, you can see the list of algorithms. There's some example, database, and so on. It's very easy to use. This is the software if you want to use. It's very easy to use. You choose an algorithm, you choose the input file, the output file, you choose the parameter, you click run, and then you see the result. You will find some rules and so on. So it's not complicated, it's in Java, but if you use other language like Python and something else, I think it will not be difficult to connect also with our library. Our type of rules, sequential rules, has been used in many applications. I just want to mention this. It has been used in e-learning. It has been used in manufacturing simulation, quality control, web page prefetching, embedded system, and many others. Okay. So that's all for my presentation. Also, one last thing I want to say is that there are extensions of this work. We did other papers after this, like rule growth. Here we have a window constraint for the rules. So that means we want to find the rules, for example, appear within 4 or 5 events. We set some maximum amount of, we can say like time between the events in the rules, for example. Another algorithm is to find the top k rules that appear the most often, to find the non-redundant rules, and so on. There are other works, and also there's a lot of possibilities if you want to do research on this topic. So that's all. Thank you for listening.